Hello friends, continuing with the chapter of nucleus, today we come to its seventh part, laws of radioactivity. Today's topic is laws of radioactivity. We will take up two laws. In the first phase, we will take up displacement laws, and in the second phase, we will take up disintegration law. First, we take up displacement laws. First law: when a radioactive element emits an alpha particle, it is converted into another element with atomic number 2 less and atomic mass 4 less than that of parent element. Consequently, the place of new element in periodic table is shifted 2 groups lower, that is left of original position. I repeat, when a radioactive element emits an alpha particle, it is converted into another element with atomic number 2 less and atomic mass 4 less than that of parent element. Consequently, the place of new element in periodic table is shifted 2 groups lower, that is left of the original position. For example, XII, a radioactive element, when emits an alpha particle, it becomes Ya minus 4 Z minus 2. So here atomic mass reduces by 4 and atomic number reduces by 2. Now let us take a practical example. Uranium-238-92, when emits an alpha particle, it is converted into thorium-234-90. Here atomic mass A, which is 238 initially, reduces to 234, less by 4. And atomic number, which is initially 92, reduces to 90, 2 less. So this is how the first displacement laws we state. Now let us take up second law. When a radioactive element emits a beta negative particle, that is electron, it is converted into another element of atomic number 1 greater than that of parent element but of same atomic mass. Consequently, the place of new element in periodic table is shifted to 1 group higher. I repeat, when a radioactive element emits a beta negative particle, that is electron, it is converted into another element of atomic number 1 greater than the parent element but of same atomic mass. Consequently, the place of new element in periodic table is shifted to 1 group higher. Now for example, XIZ, a radioactive element, when emits a beta negative particle, it becomes YAZ plus 1. Here A remains same, but Z increases by 1. Practical example, when thorium-234-90 emits a beta negative particle, it becomes thorium-234-91. Here 234 remains 234 and 90 becomes 91, that is increases by 1. Now this is how we state second displacement law. Actually, what happens inside nucleus is a neutron decays into a proton, an electron and an antineutrino when a radioactive nucleus emits a beta negative particle. That is, N10 is converted into P11, that is proton, plus an electron plus antineutrino. This is what happens when a radioactive nucleus emits a beta negative particle. Now, third displacement law statement: when a radioactive element emits a beta positive particle, that is a positron, it is converted into another element of atomic number 1 less than the parent element but of same atomic mass. Consequently, the place of new element in periodic table is shifted to one group lower. I repeat, when a radioactive element emits a beta plus particle, that is a positron, it is converted into another element of atomic number 1 less than the parent element but of same atomic mass. Consequently, the place of new element in periodic table is shifted to one group lower. For example, when XAZ emits a positron, it is converted into YAZ minus 1. Now, practical example, thorium 23490, when emits a positron, it becomes thorium 23489. Now, here mass, atomic mass 234 remains 234, but atomic number Z reduces by 1 and becomes 89. Now, actually, what happens inside a nucleus is a proton decays into a neutron, a positron and a neutrino when a radioactive element emits a positron, that is P11 proton is converted into neutron and 10 plus a positron plus a neutrino. Okay. So, these are three displacement laws which we are to learn and understand. Now, we come to second phase, disintegration law. Now, disintegration law statement: rate of disintegration of a particular radioactive element is independent of physical and chemical conditions, depends upon number of atoms present at that instant of time, and decay is exponential. I repeat, rate of disintegration of a particular radioactive element is independent of physical and chemical conditions, depends upon number of atoms present at that instant of time, and decay is exponential. Now, mathematical expression. Mathematically, rate of disintegration, say R, is equal to dN by dt, which is directly proportional to Nt, where Nt is number of atoms present at that instant of time. Or we can write dN by dt is equal to minus lambda into Nt, where lambda is disintegration constant. Minus indicates reduction of number of atoms with time, that is Nt is less than N0. Now, let us define disintegration constant lambda. Now, first we take up its definition. Now, from above equation, that is dN by dt is equal to minus lambda Nt. We have lambda equal to dN by dt by Nt, or we can write it as dN by Nt into 1 by dt equal to probability of decay per unit time, and is defined as probability of decay per unit time of a radioactive element. I repeat, what is disintegration constant? I repeat the definition of disintegration constant. It is probability of decay per unit time of a radioactive element. Okay. Now, SI unit of disintegration constant is per second. Now, SI unit of rate of disintegration is disintegration per second. disintegrations per second, DIS SEC minus 1. Now activity. What is activity? Let us define. The total decay rate R of a sample of one or more radionuclides is called as the activity of that sample. I repeat, the total decay rate R of a sample of one or more radionuclides is called as the activity of that sample. SI unit of activity is becquerel. 1 becquerel is equal to 1 decay per second. An older unit, Curie, CI, is still in common use. 1 Curie is equal to 3.7 into 10 raised to power 10 disintegrations per second. That is 3.7 into 10 raised to power 4 Rutherfords. 1 millicurie is equal to 3.7 into 10 raised to power 7 disintegrations per second, and 1 microcurie is equal to 3.7 into 10 raised to power 4 disintegrations per second. Now, number of atoms at any instant of time. The number of atoms at any instant of time of a radioactive sample are given by the expression Nt is equal to N0 into e raised to power minus lambda t, where Nt is the number of atoms at any instant of time t and N0 is the number of atoms at t equal to 0, that is at the beginning. Now we derive this expression Nt is equal to N0 e raised to power minus lambda t. The disintegration law can be expressed as dN by dt is equal to minus lambda into Nt. Let us mark it as equation 1. From this equation, we can have dN by Nt is equal to minus lambda dt. Let us mark it as equation 2, where lambda is disintegration constant and minus shows, of course, reduction in number of atoms. Integrating both sides of equation 2, we get integration dN by Nt is equal to minus integration lambda dt. Now after integration, we get log Nt is equal to minus lambda t plus log A. Let us mark it as equation 3, where log A is integration constant. Now applying boundary conditions, that is when t is equal to 0, then Nt would be equal to N0, where N0 is maximum number of atoms in the given radioactive sample. Now substituting the value of integration constant in equation 3, we get log N0 is equal to minus lambda into 0 plus log A, or log A is equal to log N0. Now substituting the value of log A in equation 3, we get log Nt is equal to minus lambda t plus log E N0, which can be written as log Nt minus log N0 is equal to minus lambda t, or we can write log Nt by N0 is equal to minus lambda t. This is logarithmic formula. We know in mathematics we can write log Nt by N0 equal to log Nt minus log N0. Now from here we get Nt by N0 is equal to e raised to power minus lambda t, or Nt is equal to n0 into e raised to power minus lambda t. Let us mark it as equation 4. Now equation 4 shows that decay is exponential and gives number of atoms at any instant of time. Now here you can see the graph. This graph is NT versus T graph, which clearly shows that decay is exponential. Assignment 13 continued. Question number 19. State displacement laws of alpha particle, electron and positron emission. Illustrate each with an example. Also clarify what actually happens in the nucleus for shift in position in periodic table. Question number 20. Define disintegration constant and give its SI unit. Question number 21. Define activity of a radioactive sample and give its SI unit. Question number 22. State disintegration law and show mathematically that decay is exponential. Thank you so much. Next time we'll continue with this topic and we will take up next part of it, half-life and mean time of a radioactive sample. Till then, goodbye and good luck to you.